Right, thank you for coming along today. Second of two lectures in this introduction to pattern recognition. Last week we got up to slide number 87 here, if you're following the slides. I just want to say a few things about the differences between detection and verification and recognition, particularly in the context of face recognition, before we get into machine learning. So detection is about finding patterns of some class in the data. In the case of faces, that's is the input pattern a face or not, so finding face regions in images. Verification is about comparing an input pattern with a specified stored pattern. Is the input face person A or is it not person A? Recognition, however, is comparing an input pattern with n stored patterns in a database and saying, in the case of faces, whose face is that in the input? And the context of each of these applications is quite different, and a very common failure to understand the differences between these leads to unrealistic expectations of the systems, a lot of wasted money and a lot of reduced security, as I will try to explain. So detection, in the input we're looking at a particular region of an image, potentially the whole image. There either is a face or there isn't, and the output is either face or no, there's no face. If we get it right, if there is a face, it's a true positive. If there's no face and we get it right, then that's a true negative. There are two types of errors that this system can commit. One is a false positive, saying that there's a face present when there is no face present, and the other is obviously a false negative, which is missing a face in the input. Usually, precision and recall are the two main indices used to express these. Precision is all about how many false positives your system makes, and recall is about how many it misses, how many false negatives. Okay, so in the case of verification, where we have a face and we are comparing it to one specific entry in a database. So we're saying the input is person A, either that or it's not person A. The output is either the system says, yep, it's person A, or it says, no, it's not. So again, we've got true accept and true reject in the cases where the system gets it right. False accept, false reject in the case where the system makes a mistake. The false accept rate here is the probability that some other person is accepted as person A. So an imposter is accepted as person A, and that has obvious security implications. The false reject rate is the opposite thing, where person A, although person A is registered in the system and the person in the input is claiming to be person A, the system doesn't agree. Okay, so false accept rate and false reject rate. The most important one is the false accept rate. So for this type of system where you're doing one-to-one matching, the balance between the false accept and the false reject rate depends on the sensitivity of your system. So we tend to use a threshold here. So for example, if the similarity between the input image and the person's data is above a certain threshold value, then we'll call it an accept. If it's below that similarity threshold, then it's a reject. So as the threshold increases here, the number of accepts falls and the number of rejects rises, both true and false. As the false accept rate falls, as the threshold gets larger, and the false reject rate rises, there's a point where the two cross, and that's known as the equal error rate, which is an easy way of, a simple one number way of characterizing how good a verification system is. So these are linear scales. If you put the thing on a log scale here, it makes it a bit easier to see down at the bottom end. You can equally well, you can plot false accept rate against false reject rate, and then you get a thing called the receiver operating characteristic, which is this. Okay. In the case where you're doing face recognition, that's to say where you're matching an input against n faces in a database, the types of error that you can commit increase. So true accept, false reject, false accept, true reject, these are as they were for the verification scenario. But now we also have somebody who is registered in the database but is not the correct person. So we have misidentification to worry about as well. And if you look at the false accept rate for this type of system, this is the probability that an unregistered person is recognized as any one of the n registered people. And relative to the simple verification one-to-one false accept rate, the false accept rate with a suffix n there looks like this. And suffice to say, it's larger than the false accept rate in a simple one-to-one verification system. You can say the same kind of thing about false reject rate, and then this misidentification rate here, where your person in the input is recognized, but as the wrong person. Okay, so this is the statistic to worry about here. I'll try to explain why. If you assume, for example, a system with a 0.1% false accept and false reject rate, where it's used in the context of verification, one-to-one matching, 1 in 1,000 times it gets it wrong. If you apply that same system naively to recognition, trying to identify any of n people in the input, if you have 100 people in your database, your false accept rate is going to go up to nearly 10%. 1,000 people in your database, 63% of the time the system's going to be wrong. 10,000 people in your database, your false accept rate is 99.9%, and so the utility of the system is almost nothing. So it's not only the number of people in the database, however, that is a problem for this kind of system. If you're computing distances from all input faces, potentially to all registered faces, the same effect happens if you multiply the number of people in the input. You're going to make mistakes that more frequently. So although verification, for example, at passport control, where you have person A's passport being compared with person A's face, or stored data, that works pretty well because it's controlled conditions, one-to-one matching, but you have almost no chance of spotting people, for example, passing through an airport, even a fairly small database of people, because the system gets swamped with false positives because of this. This happened after the terrorist attacks in the US in 2001. A lot of airport management panicked and said, we've got to do something, anything, doesn't matter what, do something. And they installed face recognition systems in a lot of US airports, which companies were only too keen to sell them. And the idea is that these were hooked up to databases from the FBI of potential terrorists and so on. The task, as I've just tried to explain, is impossible given the number of people coming through the airport, number of people in the database. Can't do it. So this very badly damaged the reputation of face recognition for several years, and it damages airport security as well, because people think they've got a level of security that they don't. And the ACLU, the American Civil Liberties Union, said face recognition is all hype, no action, doesn't deliver, waste of money, simply ineffective and of no value. Which that was true then. It's not so true now, but it was true then. But the important thing is that you need to restrict both the number of people in your database and the number of people appearing in the input that you're trying to match against the database in order to get these things to work reliably, as well as using invariant and robust methods so the system's not affected by lighting and face pose and so Now we are seeing some pretty significant progress on face recognition. Applications like Facebook tagging, you've already got a big labeled data set, and some of the newer learning methods can deal very effectively with that kind of data. And which brings me nicely onto machine learning, which is the final section in this course. There are, broadly speaking, two types of machine learning, supervised and unsupervised. Learning means that the training data is labeled with the correct answer, so which class each training vector belongs to or whatever. So you might be training non-parametric or parametric classifiers. A simple example is LDA that we covered last week. A non-simple example, which we'll get onto a bit later, is the thing called the support vector machine, which is the kind of archetypal supervised classifier. Unsupervised learning, the training data is unlabeled, and the task is to find structure, patterns in the training data without being told, or at least without being told everything about the classes. So you might have to estimate the number of classes or clusters as well as class membership, estimate parameters of models. A simple example was PCA that we did last week. A non-simple example that we'll cover in a moment is expectation maximization. So, clustering. This is unsupervised learning, and we're going to look at mixture models which represent the data as a mixture of a number of per cluster models. So if you look at this data, it kind of looks like there are two clusters there. It's easy to see for us, much less easy to reach this conclusion with an algorithm reliably. But it's natural to model data of this type as a mixture model with one mixture component per class or cluster. So this looks like a two-component model here. Simplest clustering algorithm of this type is a thing called k-means. So you're given big N data points, xn, and a fixed number of classes k, which is less than the number of data points. And your problem is to find the set of class prototypes, or the class means, the centers of each class, and the assignments of the nth data point to the kth class for all the data points. Every point gets assigned to exactly one class. So these class affiliations add up to 1. And so this thing is a 1 if the nth data sample belongs to the kth class, and it's a 0 otherwise. So you've got a matrix of zeros and ones there. And the objective function, this error function here, this is what we're going to try to minimize, and it's the weighted sum of the squared distances between each sample and the class mean that it's assigned to. Okay, so I've just rewritten this up the top here so you can look at it. The solution, the k-means algorithm, involves first you randomly initialize the class centers. You do get to pick how many there are. You don't have to work that out for yourself. And then we alternate so-called E and M steps. I've called them E and M steps because of the EM algorithm, which we'll get onto later, and these are very analogous to the steps in the EM algorithm. So randomly initialize your class prototype or class means. Then the E step involves minimizing this error measure with respect to the assignments of each sample to whichever class. You leave the class means where they are, just change the class labeling of all the training data. Then the M step involves, again, minimizing this error measure by moving the class centers around, the class prototypes, but keeping the assignments that you just set up here fixed. Then you go back and do this two-step procedure again and again until nothing changes. Okay, so the E step involves minimizing this thing involves assigning, if you do the follow through the maths, assigning each sample to the nearest, the shortest distance class. That looks like that mathematically. And then the M step involves recomputing the class means as the means of the data points assigned to each class in this step. And here's a derivative, and you set that to 0, and it gives you this solution for the class means, which is just the average overall members of that class. Easier to look at a picture. So here's that data set. Here are two randomly initialized, actually deliberately badly initialized class centers. The first E step, we assign to the blue class all the data points that are nearer to the blue class center than the red. And we assign to the red class all the data points that are closer to the red class center. Okay, so then the class membership is all these belong to the red class, all these belong to the blue class. Then we move on to the first M step, where we move the class centers. So we move the red class center from there to the mean position of all these red points, which is there. And we move the blue class center from there to the mean position of all the blue points, which is there. Okay, so do that, and then repeat the E step. Relabel the points red or blue, depending whether they're closer to the red class center or the blue class center. Repeat the M step. So we move the class centers again, repeat the E step, repeat the M step, E step, M step, and by this time, this has pretty much converged. You can keep doing this now and nothing will change. Okay, that's how that works. This is what the error looks like at each stage. First E step, first M step, that gets rid of a lot of the error, and then just run this thing until it doesn't change. Right, so that's all very good when you're assigning each of your training vectors to a specific class. Gaussian mixture models are a bit less binary, they're more analog, if you like. So now we're going to model a probability density of each class as a Gaussian. And so we model the whole data density as a mixture of these k Gaussians, one per class. And so this is a sum. The probability of a particular data point or vector x is going to be a sum. These pi k things are they're called mixture coefficients. So that's a mixture coefficient for the kth class times, this is a normal density, a Gaussian density with a mean at mu k. Covariance matrix is sigma k. Okay. Mixture coefficients are positive and they add up to 1. That just keeps the area under this density equal to 1, which it has to be to be a valid probability density. You can interpret these mixture coefficients as prior probabilities of each class. And if you do, then the posterior probabilities, the probability that a particular x belongs to the kth class, looks like this. Here's the density of all the data from up here, and there's the prior, which is this thing, and this is the likelihood of the data, which comes straight from the normal distribution for that class. So here you've got mixture coefficient times this density over the sum of mixture coefficient times density for all the classes. Okay. So what does that look like? In one dimension here, we got 3 blue Gaussians here, and the sum of these things is the red thing at the top. So that's the density of the whole data. In this case, this is the same data we were just looking at in 2 dimensions. If we only had one class, our Gaussian model of it would look something like this, with a peak in the middle and then falling off towards the edges. If we have 2 classes, then the density looks like a mixture of these, which you can tell intuitively is going to be probably much better than this. Here's a situation where we've got more classes The weighted sum here are the weights. Weighted sum of them looks like that, and this might be an example of the density of the whole thing. So we use a thing called the EM algorithm to estimate the parameters of these models. You can introduce, again, these are so-called latent variables now that control which class was responsible for generating the nth data point. Kind of like the class membership in the k-means classifier, or k-means clustering, excuse me, but slightly different. These are things that are binary again, as they were previously, but now we have a probability on each of them, which is the probability that vector n, the nth vector, belongs to the kth class, given where it is. And if you do the math, that's what these things look like. So you estimate the class means and the class covariances plus the mixture coefficients using the thing called the expectation maximization algorithm. EM is more general actually than just this kind of Gaussian mixture model, but it's most often used to estimate the parameters of this kind of model. So the thing that we're trying to maximize now, rather than minimizing an error measure as we were with the k-means, we try to maximize this. This is the log likelihood, which is the log of the probability of all the data given all the mixture coefficients, all the class centers, and all the class covariances. So the probability of everything given everything, more or less. We initialize the parameters randomly. These are the mixture coefficients, the class centers, and the class covariances. And then, just like in the k-means algorithm, first thing is the E step. We evaluate the responsibility, the likely responsibility of each class for each data vector, based on the current set of parameters, these guys up here. And then M step estimates an updated value for each of those parameters without changing these. And we alternate these two steps again. So it's pretty much like k-means, but it's a bit more analog. Okay, the M step parameter updates look like this. These are the new class mean in terms of the data, that's the xn, and these are the probabilities that the nth vector came from the kth class. Class covariances look like this, and this is a weighted mean of the data according to the probabilities that it belongs to each class. This is a weighted mean of the outer product, that's a transpose up there. So this is an outer product within the kth class, describes the ellipse that shows how the class covaries. And the mixture coefficients, the updated version, is just an average of these updates here. So this is what it looks like in picture terms. Again, we're starting off with spherical, that's to say covariance matrix is diagonal, with spherical classes centered deliberately badly to illustrate the algorithm. First of all, we assign, just like the k-means algorithm, we assign class membership to each of these data points, but now that class membership is analog rather than binary. So the more blue a data point is shown here, the higher the probability that it belongs to this blue class, and the more red it is, the higher the probability it belongs to this class. And in the middle there, they're kind of half and half, equal probabilities that they came from each class. So that's the first E step. Then we do an M step where we update the centers and the covariances, that's to say the shape of each of these classes, and they look like that. And then here are some subsequent steps: 2 iterations, 5 iterations, 20 iterations. By the time we've got to 20 iterations, this has pretty much converged, and you've got one Gaussian here representing this class and another Gaussian here representing this class. Okay. This is the same data. This is actually from the Wikipedia page, trusted source. And this shows slightly different initialization to the one that we were just using in the past picture, but you can see how the classes converge. Okay. It's true to say, as you might suspect, probability densities needing estimating, that EM requires more computation on each iteration than a simple k-means clustering. And it also requires more iterations to converge. However, so why bother? The reason for bothering is that for classes which have different distributions or they're significantly non-symmetrical, non-circular, non-spherical, EM will give you a much better result. You can use k-means clustering to set the initial parameters for EM so that it converges faster if you start it from a better position. However, both k-means clustering and EM can get stuck in local optima, so you can't absolutely guarantee that you can't prove that you'll find the global optimum. Another problem is numerical instability. For example, if a data point lies bang on one of the class means, then this can cause instability and makes that class effectively useless. There's a more general framework for EM involving latent variables, but that's beyond the scope of what we want to talk about here. So that was EM. Support vector machines. These were, until recently, the biggest development in pattern recognition for about 30 years, until deep learning either came along or came back, depending on your viewpoint. They were invented by a Russian guy who, last I heard, was in the UK, in London, called Vladimir Vapnik in '79, and the more recent soft margin SVM was published in '95, so it's about that old, about 20-something years since the soft margin version came out. Support vector machines are everywhere in pattern recognition. They're applied to many supervised learning problems. And they tackle problems with nearest neighbor classifiers, including overfitting that we talked about last week, excessive amounts of computation, nonlinear decision boundaries. They can do all this stuff. And importantly, for implementation, there's free open source software. libsvm is the most common library for this. MATLAB, OpenCV, computer vision library also have this stuff. Most of it's based on libsvm. I think the pointer's going to die, so I'm going to get a new pointer out. Hopefully this one will be better. There we go, change of color too. Okay, so the object of a support vector machine is, here we've got some linearly separable classes. This is now supervised learning, so we've got class labels on our training data. You can see here these classes are linearly separable, and any of these hyperplanes here would do it. But they have different generalization performance when new data comes in. The so-called maximum margin hyperplane, which is this red one down the middle here, down here, has the best generalization performance. The margin here is the distance between these planes. If we were attempting to maximize this margin. Okay, so we assume the classifier outputs are, call them -1 and 1 for the two classes. Then a hyperplane that separates them is this. This W0 is less than 0, I think is not true, actually. I think that came from a different example, but anyway. Because you can arbitrarily scale the weight vector W and the bias vector, bias constant W0 here, because you can arbitrarily scale those things, you can choose to set, so this is this product is 0, you can set it to 1 at this margin hyperplane and -1 at the other margin hyperplane. And if you do that, then the margin M here is 2 over the length of the weight vector. And maximizing that margin is then equivalent to minimizing this thing, which is the squared or half the squared length of the weight vector, subject to one of these constraints per data point. Zi is 1 or -1, depending which class the data point belongs to. And what these constraints effectively are, so this product is going to be greater than or equal to 1. Just going back here, it's going to be equal to 1 for points that are on the margin hyperplanes, this point and this point and this point, and not quite that one. And it's going to be greater than 1 for these guys up here, and it's going to be greater than 1 because it's multiplied by the -1 for the class membership for these down here. Okay. So this problem, this constrained minimization, it's a quadratic constrained minimization. There's a unique global solution which can be found. The thing is that only the several constraints for which this thing is exactly 1 are active. What that means is that, as you can see here, the only points in the training set that affect the solution are the ones on the margin hyperplanes. Doesn't matter if you move that point around, so long as it stays that side of the margin hyperplane, it has no effect on the solution. If you move this point around this side, it has no effect. So you only need to worry about the solution is determined only by these points on the margin hyperplanes. And those are called support vectors. That's where the thing gets its name from. For details of how this works, see the textbook. I won't go into lots of detail about these. So that's fine, but what do you do if the data are not linearly separable? One thing you can do is introduce so-called slackness, relax the constraints and allow a few wrongly classified samples. That's where the so-called soft margin SVM comes in. Another thing you can do is you can map the data into a high-dimensional space where they're more likely, as can be shown by a thing called Cover's theorem, to be linearly separable. The trick to avoiding having to do all these inner product calculations in a high-dimensional space, which could be very expensive, is a thing called the kernel trick, whereby replacing this inner product of potentially high-dimensional or even infinite-dimensional vectors, you replace it with a kernel function. And there are several kernels that are commonly used. You can also combine these and do both. So here's what that looks like. Here's our input space. The two classes are not linearly separable. After they're mapped into a high-dimensional space, they become linearly separable, and here's our maximum margin hyperplane down there. Mapping that back into the original space gives us this. Okay. This is an example of using a Gaussian kernel to do our kernel trick. So this thing now, this bold black line here is the maximum margin hyperplane in a higher dimensional space, a notional higher dimensional space. We've got some red data points and some blue data points. This is one of the margin hyperplanes with these support vectors with green circles on them. Here's the other maximum margin hyperplane with support vectors here. Okay. What these contours look like depends on what kernel function you use. Gaussian, this is radial basis functions, are particularly well behaved in a lot of applications, so they're quite commonly used. Okay. Final example with support vector machines. This is a soft margin support vector machine, again a Gaussian kernel, and here is our maximum margin hyperplane. Here's one of the margin hyperplanes, and here is the other margin hyperplane, and here. The support vectors have these kind of grey rings around them, and you can see there are some dark blue and dark red data which are inside the margins and correctly classified. Then there are some light blue and light red, kind of pink data points here, which are within the margin, and they may even be wrongly classified. So by allowing wrong classifications and allowing data points to leak into the margin area, we can end up with a relatively smooth boundary, whereas if you were to try to fit this data with such that you got a lower error, you might end up with a much nastier boundary. So the details of this are a bit beyond the scope of this course, but you can go and read up on support vector machines if you're interested. I'm going to press on because we've got quite a lot to do. Neural networks. This is now the kind of third age of neural networks. They were popular in the 60s, popular again in the 80s, and now they're really coming into their own. Most of what people call AI these days actually means neural networks. The original neural network was based on a thing called the perceptron, which is a very simple system, loosely based on a model of nerve cells in the brain. And it's a linear combination followed by a nonlinearity. So here's linear combination, a weighted combination of inputs xi, plus a bias weight w0 there. And this function f is some kind of nonlinearity. Like this. Okay, so write this as an inner product between a weight vector and input vector. Looks like this. Here's the bias. We just have an input of 1 and then do this weighted sum. This signal at this point, which is effectively the inner product of the input vector with the weight vector here, is known as the activation of this unit, and we'll get back to that soon. And here's the nonlinearity. You can use anything, but originally people used step functions, or linear rectifiers are quite popular. If this is continuous, and so you can differentiate it, that has advantages that we'll see. Okay, so a single layer of these things, or a single perceptron, in fact, single unit, can implement a linear decision boundary. So if you assign -1 or +1 when this thing is positive or negative, you can do a classification like this. Here's an input vector, here's our weight vector. This distance here is the inner product of the two. Here's bias, just shifts the thing in this direction. And here you'll get a positive output if the thing is to the right of this line, and you'll get a negative output if it's to the left. So it's a simple linear decision boundary. And that can solve simple problems like the AND problem. Here's input number 1, input number 2, and these are the desired outputs. Obviously you need 2 1s in the input to get a 1 in the output of an AND gate. You need a 0 in both inputs to get a 0 out of an OR gate, so it looks like this. Exclusive OR, where you need either no 1s or 2 of them to get a 1 out. That's not a linearly separable problem, so a single perceptron can't solve it in 1 layer. So you need 2 layers. In general, if you have a 3-layer perceptron, you can show that you can solve, in theory, any decision boundary. You can create any decision boundary in your input space that you like. Here's some inputs. There are 3 layers. The input layer is fully connected. These are all shown fully connected, actually meaning that every unit in every layer is connected to every unit in the next layer. So the first layer here computes hyperplanes like we just saw, simple linear decision boundary. Then we have a layer of AND functions which effectively just computes regions bounded by these hyperplanes, and then an OR layer can compute a union of these regions. So if you have enough units, 3 layers is enough to create an arbitrarily complicated decision boundary. How do you train these things? Well, the learning rule is a thing called the Woodrow-Hoff rule or delta rule. And the idea is that if an input vector x is misclassified, you need to change the weight vector. You don't need to do anything if all the data is correctly classified. So if your desired output is t and your actual output was y, so that your error is this thing called delta, t minus y, the learning rule is that you increment, slightly shift the weight vector by this thing, which is some constant times delta times the input. And that's why it's called the delta rule, this thing. So in this example, here's our weight vector w, and that creates a decision boundary down here, which separates classes A and B. Now, in this example here, this input vector x is from class A, but it gets wrongly classified as B because it's this side of the boundary. So the way to fix that is to change the weight vector, update the weight vector by adding this increment to it and shifting it round, rotating the whole hyperplane. And then you'll classify the new sample correctly. Okay. If you have a multi-layer perceptron and it has the non-linearity of each of these cells is differentiable, then you can propagate the error from the output back to earlier layers and train the whole network. So here's the output, looking at the whole output layer here, taking that as one big vector. That's, where are we, t. The desired output, sorry, is t. The actual output was y. So this is a simple squared error measure. Then we can define for the ith unit, we can define this thing called sensitivity, and there's a reason for using the delta symbol that you'll see. Sensitivity is how that error at the output changes with the activation of the ith unit. The activation, you may remember, was this thing, the signal at this point here. Okay. So for an output unit, this is a unit in the output layer, the most right-hand layer. The sensitivity here is, you simply differentiate this thing with respect to the activation, and you get this thing. So this is the slope of the nonlinearity in those output units at the particular activation value times the error in that unit's output. A thing called the generalized delta rule then gives the weight update. This is for all weights in a particular layer in the kth layer. I'm sorry, that's the kth unit in this layer. Is alpha times delta k, which is the sensitivity of the kth unit times the input vector x. Okay, and that looks like this if you're talking about a unit in the output layer. So x here is the input vector to all units in the same layer. All units in the same layer have the same input vector. So that was the output layer. That's fairly easy, but what do you do about non-output layers? Well, you can establish that the sensitivity of a non-output unit, which is this thing, can be determined by the weights that connect it forward to the output units, and these are the sensitivities of the output units. So this is a sensitive and output unit. Here's the weight that connects that unit back to the previous layer, and this is the activation of a unit in the previous layer. Okay, with that I'll break out a picture in a minute. Here we go. Unit K in the output layer, unit J one layer back. These weights, these three weights here are the weights from unit J there to unit K there. Okay. Right, so this is where the term error backpropagation comes. The learning algorithm is called error backpropagation or just backprop. If you hear people talking about backprop, this is what they mean. And the generalized delta rule then for a non-output unit gives the weight update as this thing. Again, it looks much like the original delta rule because it's something times delta, which is now the sensitivity of that unit, times the input vector. So you throw all your training data at the network, so X takes on the value of each of the input vectors, and you compute the weight update for each of those. Okay, so that's how that works. Neural network, when people say neural network, they normally mean multi-layer perceptron trained with backpropagation. This is usually what neural networks mean. So going back to this picture again, output layer weight update looks like this. This is the error in the output, desired output minus actual output when the input, excuse me, when the input was X. Going back to the previous layer, that again is the sensitivity of the output unit K, weights connecting it back, that's these three weights here connecting back to this Jth unit in the middle layer here. And this thing is the weight update for the weight vector going into unit J. That's this weight vector here in that ellipse. Okay. So that was backpropagation. How are we doing for time? I think we're okay, actually. 1, 2, 3. We might even finish early at this pace. Deep learning. You will have heard a lot about deep learning and AI, as people have started calling it. AI used to mean something else. It used to mean rule-based systems back in the 60s and 70s, but now people say AI, they pretty much mean deep learning. And these are neural networks, usually trained with some kind of backpropagation. Right now, image and speech recognition, data mining with large and or difficult training sets, sometimes labeled and sometimes not labeled. People are throwing neural networks at all this stuff now. It is probably the most active research area in this field, easily by a long way. People like Google, Facebook, Microsoft Research are throwing huge amounts of people and money at this problem now. The most often used type of neural network is a thing called a convolutional neural network, and what that means, if you remember convolution, back last week we looked at sweeping a filter across an image, not changing the filter weights, but just sweeping it across the image uniformly. In a neural network, a convolutional neural network is one which has the same weights at each cell. So the weights of this cell here are going to be the same as the weight vector of this cell here and this cell here and this cell here. And that makes the output of a particular layer be effectively a convolution of the weight vector that's shared by all the units in that layer with the input. So that's why they're called convolutional neural networks. They're called deep neural networks because they have way more than the 3 layers that we just looked at. Weights, as I've just said, weights are repeated or shared across all the units in a layer. You can have multiple layers, as it were, within each layer, but each of those has a common weight vector, which makes them shift invariant, means that the signal is processed the same way wherever it is spatially. So an object appearing, say, in this part of the image, here's an image, object appearing in this part of the image will be treated the same as an object appearing in this part of the image because the weights are shared between all the units. So there are usually multiple trainable convolutional hidden layers, which is why these networks are called deep networks. There's also stages where signal normalization, so the signal doesn't either get too large or too small as it propagates through the network. Maximum and average pooling, what those do is, for example, set the output of a unit in a max pooling layer is set to the maximum of its local inputs, which is kind of finding the spatial maximum locally. That reduces computation and increases shift invariance. Training is usually done by stochastic gradient descent solvers. These need, or rather the network architecture and the training requires large volumes of training data. But now, fortunately, that's possible because we have this large volume of training data in a lot of applications now. Training usually uses GPUs, that's graphics processing units, which you probably know have grown out of video cards used in PCs. And originally the idea was to speed up the image processing because image processing on video cards does a lot of shift invariant operations, and so the graphics processing unit emerged as a way of taking some of the load away from the CPU and putting some of the computational power onto the graphics card. But these things are also ideal because they're good for image processing. They're also, for the same reasons, very good for training neural networks. Random dropout. Dropout is a modification of the training algorithm to prevent overfitting. So what it means is that at each training cycle, you randomly leave several units unaffected. You don't update them. And that protects against falling into local minima. So here's all this has happened in about the last 5 years. That's how fast this has been moving. The first famous neural network, deep convolutional neural network, this guy Jeff Hinton, who's in University of Toronto, now Google have snapped him up, I think. And these people from Toronto published this thing in 2012. This is Neural Information Processing Systems Conference, which used to be a small conference, now it's big. Here's an input layer, 224 by 224, so this is a kind of typical, relatively small image size. 11 by 11 filter, convolutional filter mask. And that feeds into another layer here, which is reduced the spatial resolution to 55 by 55, but within this layer there are 96 planes, each of which has a different convolutional filter weight vector. Then there's a max pooling stage, which we just spoke about, where you reduce the spatial resolution by taking a local maximum of the input, in this case in a 5 by 5 area. Another stage here. Now we're down to 27 by 27, but we have 256 of these planes within this layer that can represent different types of signal. And this architecture gets repeated with a bit more max pooling at the end. Densely connected final couple of layers, and then that's a 1,000 unit output layer. So this neural network might have 1,000 classes of object that it might recognize, for example. That's why there are 1,000 units in the output. So this thing took about a week to train by stochastic gradient descent on using 2 NVIDIA GPU cards. This is back 5 years ago. In only, and it behaved extremely well. Got some very good results and attracted a lot of attention. One of the results of that was that only 2 years later, Google's attempt, GoogleNet, looked like this. And now instead of the 7, this had 7 trainable layers and 3 max pooling. The Google's net had 22 trainable layers and 5 layers and max pooling. This is the input at this end. That's the output down that end. The blue rectangles here are trainable convolution layers. The red rectangles here are max pooling or average pooling. And the green ones are normalization and concatenation and some other kind of housekeeping layers. There were also some additional side branches, this one here and this one here, which were used during training to keep the representations in the middle here sensible. One problem with neural networks has always been that you can see the input vector, you can see the output vector, but it's difficult to know what's being represented in the interior, the so-called hidden layers. And that's been one of the reasons why there's been some reluctance to adopt neural networks particularly for safety critical applications, because you couldn't always show what was being represented and that it would always get it right. So anyway, the idea of these layers here was to hook this up for the first bit of training and train back from there effectively, then hook this next output up and train back from there, and finally to hook up the output and train back from there to keep everything in the middle here kind of sensible. So, and keep it efficient. So this also took about a week to train on some high-end GPUs. This is the reference. Now this results are coming out so fast now that instead of waiting to have your paper published in a journal, everybody's using this archive. This is a archive preprint service whereby before your paper comes out in a journal, you put it there and everyone can look at it and respond. Okay. In 2015, Microsoft Research came out with a slightly different model, 152 layers now, but they changed the way that each layer works. By instead of learning this desired mapping, call it h of x, starting from nothing, or starting from just random initialization, random noise conditions, what they decided to do was to learn the difference between that and an identity mapping. Because the idea is that a lot of layers don't change the signal very much, and so you can approximate their function as an identity function. So rather than have to get there from zero, it's easier to assume the identity and then just learn the difference between the identity and your desired mapping. So they did that, Microsoft research people did that and got very good results, as we'll see in a moment. This ReLU thing here is a rectified linear unit. The units in this network have a non-linearity that looks like it's flat until the origin and then it goes diagonally up. So it's a very simple non-linearity, and that's called a rectified linear unit. Okay, so this is called residual learning, and again, this was published December 2015 on the preprint archive. So what's all the fuss about? Looking at object recognition, object detection and recognition, the recent history, and this is only 5 years, only the last 5 years, there was a thing called the ImageNet Large-Scale Visual Recognition Challenge, a competition that was run out of Stanford University mainly, I think. And deep convolutional neural networks have dominated that contest in the last few years. There are several different tasks in this set. There's a big publicly available set of images and some correct answers that you can use to train your networks on. And the classification task is the one that the headline act, as it were. So there are 1,000 object classes in this data set. That comes from back here, back in 2012. This was a first attempt at an entry into this competition with 1,000 classes. So top 5 error rate means that if there was only one object in the picture, you were deemed to have got a correct answer if that object appeared in the top 5 positions in your output. In other words, if the output unit corresponding to that object class was in the top 5 most active output units. So that supervision network that we just looked at from Toronto had a top 5 error rate of 16.4%, and at that time there were 6 entries into this competition, and only one of them was this convolutional neural network. But it won the competition, which attracted a lot of attention, as you might expect. The next year, 2013, 24 entries, and 17 of them were convolutional neural networks. These people from New York University got an error rate of 11.7%, so some pretty significant progress. Then the Google net that we just looked at came along. Now 31 of the 32 entries into this competition were deep learning entries, and the error rate's down to single figures. Microsoft Research comes along the next year with that residual learning and more or less halved the error rate, which is that's a very, very significant difference there. Then last year, TRIMS is the 3rd research institute of the Ministry of Public Security, Chinese government research institute, China is now probably the main locus for this kind of research, partly because the government's doing a lot of surveillance and security work. But they got this down below 3% now. Not quite such a big percentage reduction, but when you're down at this kind of level, it's really difficult to do much better. And then just 3 months ago, a thing called SE-net, which stands for squeezing and excitation, I think, won the contest with 2.25% error rate. Momenta is a self-driving car research outfit in Beijing, I think. And they were working with people from Oxford university in the UK, and they've got it down to 2.25%. Squeeze and excitation networks. Again, this appeared on the preprint archive in September. Now these values are getting so tiny that they've decided not to bother keeping this contest running, because we're really down into the kind of final couple of percent. So, but that's how quickly this field has moved over the past few years. So how about, that was object recognition, how about face recognition? Well, there was, still is, a data set called Labeled Faces in the Wild, which came out of the University of Massachusetts in the US. Not as big as the object recognition set used for the ImageNet contest, but there are about 13,000 images, including about 6,000 people, and about 2,000 of those 6,000 people had more than one image in the data set. There's some lighting variations, some pose variation, stuff that makes it difficult. And in 2014, Jan LeCun, who's one of the big noises in neural networks, and the Facebook AI group got 97%. I think this is top 5, but I'm not sure. I think it's top 5. Correct. Then National University of Singapore and Baidu, is the biggest Chinese search engine, came along the next year and hit 99.7%. Google came along the same year and also hit 99.7%. So where do you go from there? Well, the data set is really too small to test very large scale recognition. There are bigger labeled data sets, but they're not public, such as Facebook's huge number of tagged images, which is very convenient for Facebook, but not so great for everyone else. But there are now more public data sets being built with, so they're wider, meaning more people, and they're deeper, meaning more parameter variation per person. There's now a new data set coming out. This is National Institute of Standards and Technology in the US. It's only 500 people, but each person has multiple images, and several people have some video in there as well. They require this kind of architecture where you build a template of some description from all the training images of the same person, build another template from this person, and compute similarity scores. That's the way they've decided to run their contest. So the pose and illumination and lighting variations are more difficult than the old labeled faces in the wild set. Even so, the Oxford team in last year got 92.8% rank 1. That's the most similar person in the data set being correct. If you allow them to, if you call it a correct hit when they get someone in the top 10, then that's 98.6%. This year, University of Maryland took that up a bit to took the rank 1 value up a bit, 93.2. This one actually fell. Their rank 10 accuracy actually fell for complicated reasons. Then National University of Singapore and Panasonic R&D in Singapore very recently hit 96.4 here, 99.2% on rank 10. So this is now getting saturated. And that's their paper. I think that's the NUS paper. That's from April, actually, April 2017. NIST, that's the same NIST as here. It's a US government organization. They used to do a face recognition test. They stopped for a while, but now they've started again with a different test. And NEC of Japan, obviously, won this test. NEC's recognition stuff is used in airports in Japan now for passport checks and when you do your fingerprints and face recognition when you fly through Narita or Chubu or Kansai or whatever, that's NEC's kit doing that. NEC have said that their new algorithm that won this year's NIST vendor test does include deep convolutional neural networks, but they won't say anything else about what's in there for obvious commercial reasons. So you can say, it can now be said that deep convolutional neural networks are now better than people at recognizing stuff under controlled conditions like in an airport passport verification system where you're just doing verification, controlled lighting, frontal pose, no expression. Humans are still slightly better than neural networks under difficult conditions. For example, figuring out that these are the same person or that these are the same person, or more difficult examples, age differences, haircut differences and so on. But humans are still not as good as we think we are. Actually, humans are surprisingly poor at recognition. Okay. Why is neural network performance now so good? Well, mainly because there are more complex data models being learned by these very deep and wide neural networks. There's much more training data available courtesy of the internet. There's now distributed large-scale learning is possible. We've got faster networks, we've got GPUs, and you really need distributed learning. You can't really do this all on one big CPU. You really need a bunch of machines talking to each other to do a big recognition exercise. There are more resources available to people. For example, IBM and NVIDIA have offered free cloud and GPU training services since 2015 in the ImageNet competition. The dropout training algorithm that I mentioned earlier has been quite effective at preventing overfitting and stopping these very complicated networks from learning models that are too complicated for the data. And there's a load of open source free software for deep learning, for training your networks. Those include these. The main one is Google's so-called TensorFlow. There are several others. Here they are. They're changing all the time and they're evolving all the time. But these are all, I think these are all pretty much free. Yeah, they are. Okay. How difficult they are to use and what they're best at doing varies from one to another. So you need to go and look those up if you were thinking of applying them to a particular framework. Main current development areas are just about everything you might want to do in pattern recognition, really. Image and video recognition, faces, objects, actions, maps, terrain, road signs, you name it. Video and archive indexing. Now the amount of video that's out there on YouTube and so on is spiraling, and if you want to be able to search that video, you want to be able to label it automatically so that it can then be archive searched with a text search effectively. Automatic colorization of old black and white movies and video footage is an interesting one. Self-driving cars are obviously coming along pretty quickly. They need to do pedestrian detection so they don't hit people. They need to do traffic detection so they don't bang into each other, inter-vehicle communication, and that's, a lot of people are throwing neural networks at that. Industrial and domestic automation, so gripping and handling objects in factories, navigating around factories, process control in factories as well. Speech recognition and interpretation and synthesis is increasingly using neural networks. User interfaces, automatic translation, speaker recognition, all being done by that. Finally, games and strategy development. Google has a subsidiary that they bought a couple of years ago called DeepMind, which is in London in the UK, and they've been training deep neural networks to play Go, which is a game where you turn over black or white counters. And they have had a neural network called AlphaGo. And back here, the first one was AlphaGo, now it's known as AlphaGo Lee. And what they did was they trained these neural networks using examples of games previously played by human Go champions. So this guy, Lee, was a Go champion, and the machine trained using examples of his stuff achieved this green line level of accuracy. I'm not exactly sure what the accuracy measure is up here, but anyway. And this is, the machine ended up beating the Mr. Lee. Then there was a later version, AlphaGo Master, which achieved a higher accuracy up here. And these were trained by using historical data. The new version now, known as AlphaGo Zero, which has just come out 2 months ago in Nature. This is the online version of Nature. I don't know whether the paper one's out yet. But what they've done here is they've ignored human examples and found that if you ignore human examples, the machine actually does better because it can learn, it plays against itself, repeat over and over again, plays against itself, learns strategies which wouldn't occur to humans, not even Go champions. So after 40 days of training, this thing surpassed all the other versions of it and is now, they claim, the best Go player in the world, and I'm tempted to believe them. So that's where we're at the moment, and that was the last slide. So we've got about 8 minutes by that clock if you'd like to ask any questions. Just a comment about the textbooks, by the way. There were 3 recommended texts for this course. The Do to Heart and Stork is the most general one of them. The book by Chris Bishop, the Pattern Recognition and Machine Learning, is bigger and more difficult. But if you want to look at the mathematics behind anything, the Bishop's book is probably the way to go. Okay, that was a quick book comment. Anyone have any questions? Any bits that you didn't understand? Yes?
About the Thomason.
Yeah.
In your slide, the various kind of feature you get as X
Yeah.
by using array tree.
Yeah.
How about using large feature as Y? I mean,
Yeah.
I would do that for output 5 or 6 feature.
Yeah.
Is it possible to use support vector machine?
Yeah, oh yeah, absolutely. Let's just go to support vector machines. There we go. So you mean, for example, in a case like this?
Down to,
Keep going.
sorry, next slide,
Next one?
next,
This one.
next.
Then we're into the perceptron there. But no, in principle, I mean, these are all shown in 2 dimensions as though there were 2 features, but these are usually much higher dimensional spaces.
I mean, it is talk about X. I want to know
Yeah.
why.
Okay, so let's just go back to here. These, yeah, okay, so X is your incoming feature vector, which could be one-dimensional if you only have one feature, could be 2-dimensional, could be high-dimensional. Does that answer your question? Not sure. I don't think I'm understanding your question, perhaps.
This is y equal.
Yeah.
Sorry, I imagine as a regression model of this.
Okay.
You make one line. So,
Right. Oh,
this y, the y is only one dimension.
right. So you mean for multiple classes, for example? Yeah. There's a thing called a multi-class SVM, which is basically one SVM per class. So you will have several different boundaries in the same space.
So using several models.
Yeah. Yeah. Either using different models or using the same model with different parameters for each class, which is probably more common. Okay. Does anyone else have any questions? I think the example class is next week at what time? Do you happen to know? Put you on the spot.
It's from
4 o'clock, right.
probably 4 o'clock, probably for break.
Same time, okay, right. So if you don't have any questions now, but you do have by next Thursday, you can always ask next time. Any bits people found particularly difficult to understand or particularly found the explanation difficult? Or feedback is welcome? Yes.
I think this class was a little bit dense, a little bit.
Yeah,
Yeah.
right. Sorry about that. Yes.
No, but
We're trying to get through quite a lot of material in only 2. Yeah. In previous years, we've done 3 lectures, which has spread it out a bit. But now it's become 2 lectures and an example class. So unless we skip quite a lot of that, it's difficult to get through it in 3 hours. But it might be worth losing some of the more difficult bits. Yeah, I'll bear that in mind for, it won't help you, but I'll bear it in mind for next year.
And forming is very difficult.
Sorry about that. Yeah. Any other questions or comments while we're all here? Okay, right, well, the clock says 6 o'clock, so that's my target finishing time. We were a bit early today, actually, but so thank you very much for coming, and I'll be at the example class next week if you do want to ask anything or ask me to explain stuff a bit more clearly or whatever. That's fine. Any bit you didn't understand, come and ask me. Okay, thanks very much.